All right, here we are on our fifth additional focus area, the first objective that relates how electrons relate to what magnetism is and tells us a little bit about magnetism. So let's jump right into it. The first thing we need to remember is something you probably learned in middle school, talking about atoms. Remember, everything is made up of atoms, all matter anyway, and that the atoms are made up of little protons. We're going to represent them with that blue there that are positively charged. In the same area or the nucleus, the middle of the atom, are some neutrons that are orange there and don't have a charge. They're considered neutral. And then around them, in what are called electron clouds, are the negatively charged electrons. We're reviewing that because it has a lot to do with why some materials are magnetized and act like magnets and some do not. And that's just showing how the electrons move around the nucleus in these clouds. It's not a perfect circular pattern. They're all over super fast, virtually impossible to tell where they are at any given moment, but they know what regions they're in. So on to the main point of this focus area of magnets. Magnets are all determined based on the atoms that they're made of. So really, it's not even the atoms, if we're being real specific. It's the electrons that are in the atoms. And if we look here, while electrons do move around an atom, like we see at the bottom here, let me get my pen. All of these multicolored one, the blue, the red, the orange, the yellow, those are electrons. They're moving around the nucleus here. They create a magnetic field. Every little individual electron over here acts like its own little magnet. And in most objects, the electrons all spin in random different directions, like you see in the picture down here, all these different arrows, meaning they're spinning in those different directions. And that means each of their little magnetic fields point in random directions too, so they all kind of cancel each other out and nothing's magnetic. And that's almost all objects. So pretty much everything. I mean, look at your desk. There's probably nothing on it right now that's magnetic. Your pencil's not, your pen's not, your phone's not, unless you have the new iPhone, I guess, the 12. But for the most part, they are not because their electrons are spinning randomly and those random directions kind of cancel each other out. However, some materials have electrons that all spin in the same direction. And remember, every electron has its own magnetic field. So these ones, like you see in the picture down there, have all the magnetic fields of each of these electrons in this object pointing in the same direction. So all of their magnetic fields are in the same direction, which makes the object have a magnetic field and act like a magnet because the magnetic fields aren't canceling out. They're all in the same direction. So now we do have magnetic properties or a magnet. So let's tie in some vocabulary with this picture here. We have three up top different materials. You don't know what they are. And we're trying to figure out how can you tell if it's magnetic or not. So material X, this first one, you can see that the arrows are pointing every which different direction, all randomly and crazy. So they're canceling each other out. Not a magnet. If you look here, these little boxed off or spaced off areas, they're called domains, and that's regions that have magnetic electrons aligned or going the same direction. So basically, think of it as little areas or domains where the arrows point in the same direction. So material X doesn't have even the domains. They're all random and crazy. Y would be magnetic, but the domains are not lined up. In other words, not all of them point in the same direction as the other one. So this points this way, this points the opposite way, some point down. So these do have domains, little boxes or areas where all the arrows point in one direction, but the arrows of other domains point different directions. Still a magnet, but a little different when we talk about the domains. Material Z over here, all arrows point the same way. And there are domains, these boxed off areas. So we would say material Z has all the domains aligned or in the same area. And it is magnetic because the arrows point in the same direction within the domains and all over as well. Why do magnets have a north and south pole? If you've ever played with a magnet and if You were here for the lab day in person when we were doing our forces and fields focus area. You got to, but we said they all have a north and a south pole. So part of the reason they all do is because you can cut a magnet in half. Some are soft enough you could easily do it. You can even break some in half with your hand, and it will still have a north and south pole. And the reason is right here, because of the domains inside the magnet. Since they all point in the same direction, there will always be a north and south pole. Look at this picture up here, the one I'm circling. Well, actually, let's look at it here. If we call this side the north pole, this the south, I cut this in half. Well, now this little part still has the north because the domain, how it's lined up, the arrows, magnetic alignment is pointing to the right, and it still has the opposite end where they're not facing or pointing, and that's the south. It doesn't matter where I cut it. I could cut it here, here. I'm always going to have one end that's the arrows are pointing the north, and the other end would be the south there. We talked about this a little bit in our forces and fields focus area, and with both electricity and magnets, like charges. So when we talked about electricity, we said like charges, like two positives, push away. They go away from each other. Or two negative charges go away. So when we say like charges, we mean the same, and they go in the opposite direction. But when I have opposite charges, they come toward each other. They're attracted to each other. Like static electricity, or if you were here the day that we put our hands on that little silver ball that was buzzing and it made gave us a little shock or made our hair stand up, same idea. Opposites attract. With magnets, we don't call them charges, we call them poles, but it's the same. Two north poles are the same. We said like poles or like charges repel, so those would never be able to touch. And if you were here the day we did the little mini lab in class, we could never get the norths to go by each other. And if we held one magnet and didn't hold the other, when the norths got by, it spun the magnet that wasn't held around. Same with south, because they're the same. But when you were playing in class with them, when you had a north and a south, those were attracted and those stuck together. We saw the magnetic field in our mini lab. We were able to draw them or saw a picture of them, but we actually were able to get our little iron filings to line up, and the magnetic field is represented by these vectors or these arrows, and it just shows the north to south connection, and then the vectors going away from the north and towards the south. And remember, that's why they attract. If I put a south over here, it's going to attract. If I put a south over here, it will attract to the north. If you've ever held a compass, and sometimes I have enough, so I'm not sure this year if we played with the compass or not, but the compass will always point north. If you're holding it, you can even have one on your phone. Some phones have an app. They always point north. You could be walking south. The magnet on the compass turns around and points toward the north, and it's because compasses are just little magnets, and the Earth is a giant magnet. So this compass needle is a little magnet, so it will always align itself with the North Pole of the Earth, which is due to, and I don't mean the North Pole like where Santa lives when you were little and thought that. I mean the North Magnetic Pole, which is actually the South Geographic Pole, which makes no sense. I know it's confusing, but the North Pole where Santa lived, pretend lived, is considered the South Magnetic Pole, and the South Pole where Antarctica is in real life is the North Magnetic Pole. So that's the direction that the compass is